Hello, in this video I will do example 5 of optimization word problem involving two adjacent rectangular corrals. So in example 5 optimization word problem, a rancher has 200 feet of fencing with which to enclose two adjacent rectangular corrals. What dimensions should be used so that the enclosed area is maximized? So first I would draw the best image. So we have two rectangular corrals. So what does that look like? So it would look like this. You have a rectangle, right? And then it's split into two rectangular corals. So this would be coral number one, and then this would be coral number two. Okay, so we're trying to find what dimensions would be enclosed area maximized. So maybe we could call this length x, and then this vertical distance y. This length here would also be x. This would also be x. This would also be y, and then this would also be x. Then this length here is just one, would technically be y, and there's only one y. Okay, so what are we given? It says a rancher has 200 feet of fencing, so that is a perimeter, right? So what is perimeter is basically you add up all the sides. So you have 1, 2, 3, 4. You have 4 x's. And then how many y's do we have? Be careful. You have one y here, you have one y here, and then you also have a vertical y here. So that's 3 y's, not 4 y's. Okay. And then you just replace perimeter with 200. Okay. So this is one of our equations. And what is our other equation? So if we look up what dimension used to close the area is maximized. So now we have to think of area. So what is an area of a regular rectangle? It's length times width. So over here, the area of the first corral, or this rectangle, is length times width, so it's just x times y. And then the area of the second corral is also x times y. Okay, so the total area of these two corrals would be 2xy's, right? Okay, so this would be my second equation, or also my primary. And then this would be my constraint. Okay, so what are we going to do next? Once we found our two equations, we're going to substitute one of the variables into the other equation. So let's start with our constraint equations. And I think we can get away with either solving for x or y. It doesn't matter in this case. So maybe I'll just solve for y. And I'm going to plug that back into the primary. So how am I going to solve for that? So it's 200 equals 4x plus 3y, and then solve for y, so I'm going to subtract 4x. Solve for y, so you're going to divide this by 3. So y equals 200 minus 4x over 3. Okay, and then I'm going to plug it back into this equation. So it's a equals 2 times x times y, which is this whole thing, right? Okay, and then if I just kind of like clean this up, boil it out, you're going to get 400 over 3x minus 8/3 x squared. Okay, so when you FOIL that out, that's what you get. Now, what we're going to do is find our critical value. So we have to take the derivative and set it to 0. So let's take the derivative in respect to x. So on the left, the derivative in respect to x would be dA over dx. Over here, the derivative 400 over 3x, 400 over 3x is just 400 over 3. Don't have to put dx over dx because that becomes 1. And then the derivative of this is just applying power rule. That would be negative 16/3 over x. Okay. Go ahead and solve for x. So you're going to set dA dx to 0 or your a prime. And I got to solve for x, so I would just get rid of the fraction first by multiplying all three sides by the LCD. And our LCD, it looks like it would be 3. So I'm going to multiply all three sides by 3. So 3 times 0 is 0. 400, 3 times 400 over 3, the 3's cancel, so we're left with 400. 3 times negative 16 third x, the 3's cancel, so we're left with negative 16x. Okay, go ahead and continue for solving for x. So I'm going to subtract 400. Divide this by negative 16. And I get 400 over 16 is 25. Okay, so 25 is our critical value or our x length, but is it going to give you a maximum value? So how do we verify this? By doing the test point method. Okay, so go ahead and put 25 in a number line. We're going to test region 1 and region 2, correct? And then we're going to do dA over dx. We're going to put it in our first derivative, which is 400 over 3 minus 16 over 3x. Okay. So let's test region 1. I need a number less than 25. I think I could get away with 0. So it's 400 over 3 minus 16 over 3 times 0 is 0. So 400 over 3 is still positive. I don't care about the number, just the sign. So you can put a plus here. And then I need a number greater than 25, so maybe I could do 26. Okay. And when I put all that together, what do I get? I get like negative 5.3. It's negative. I only care about the sign. So if you look at our sign chart, we have a positive to a minus. So according to our sign chart, if you go from positive to a minus, you have a local max. Okay, so yes, we can verify that 25, the x value 25 will give us a maximum value. So they're asking what are the dimensions should be used. So we found our x, right? Our x is 25 feet. And then how do you find your y? So what is our y value? Our y value is 200 minus 4x over 3. Which is 100 over 3. And wait, what are we in? I believe we are in B. So our y value will be 100 over 3 feet. So what are the dimensions that maximize this 2 corrals? It would be 25 feet by 100 over 3 feet. Okay, so these are our dimensions. Okay, so that wraps it up for this optimization problem.